Alright, so guys, the second portion of the video is covering area bounded by a graph, in this case the x-axis, and two vertical lines. The vertical lines are our limits of integration. They give us boundaries. So when you have area bounded between two curves, a couple of things can happen. One function is always above the other function, or the two functions change which function is on top inside the interval, in which case we'll just need to flip the functions and integrate. We'll see that on example 7. So for example 6, let's look at how the graph looks. I think I already have the graph pulled up on this calculator. So 2x squared minus 3x plus 2 looks something like this. We see that it intersects the y-axis at 2, and when x is 2, the y value is 4. So we need to draw a graph that's close to that. Doesn't have to be perfect. So we have 1, we have 2, and when we said when x is 2, so let's make this pretty wide. So 1, 2, 3, 4. So again, our graph does something like this when x is, it dips down to 1 somewhere around here. So we have two different functions. The blue function is 2x squared minus 3x plus 2. The other function is the x-axis. So the x-axis is, it's just right here. So what we're finding is the area bounded between these curves, which is this region. So now all we're taking, the area, is the difference of this curve and this curve. That would be, if we call this function f of x and this function g of x, it's just f of x minus g of x. In this case, it's always 0. So we're always just subtracting this function value in 0. So in the last video, we learned that that was just a definite integral from point A to point B. So what we want to do is integrate from 0 to 2, 2x squared minus 3x plus 2 dx. And when we integrate, we would get 2x cubed over 3 minus 3x squared over 2 plus 2x, evaluated from 0 to 2. So the only thing that gives value to this integral is the upper limit. When x is 0, all of this is 0. So while we could actually, I do want to show you how to do this on the calculator. So let's go to y equals, we'll have, let's see, alpha y equals 2/3 x cubed minus 3/2 x squared plus 2x. So now notice we put this in y1. So two ways to check the function value at 2. First, we could do second table, and at 2 we see it's 10/3. This is the easiest way. A second way to do this is to go to vars, go to y vars, go to function, put y1, and in parentheses we'll put 2, and we get 10/3. Now, I think you should still be able to do the mental math to get this, so that's what we're going to do. We just know the answer should be 10/3. So we have 2/3 times 8 minus 2 squared over 2 is 4. 4 over 2 is 2, minus 3 is minus 6, and plus 4. What's this? Negative 2. So 16/3 minus 2 is 16/3 minus 6/3, which equals 10/3. So if you have a calculator, use it. Makes the calculation much easier. We're concerned with integrating the result. For example, 7. So let's look at, I wish I had a color calculator. Let's look at two different functions. We'll say y equals sine x, and we'll do cosine x. Our limits are from 0 to pi over 2. Now we know sine and cosine only go as high as -1 and +1. We're going to make our y's go from -2 to +2, and we'll do our x's from 0 to pi over 2 is roughly 1.57, so we'll say to just 2 and graph this. So the first function being graphed is sine. The second function being graphed is cosine. So in the gray box above, we need to, it says that we need to find the intersection value if the functions intersect inside this interval. So sine and cosine do intersect in between 0 and pi over 2. To find that value, we would have to do sine x equals cosine x. You know what? We did this in a terrible order. Sine goes from 0, so we'll say pi is over here. So pi over 2 is here. So sine starts at 0, goes to 1, and goes back down, and looks like this. Cosine, on the other hand, starts at 1, goes down to 0, and goes, so from 0 to pi over 2, doesn't go down to -1. So it's going to look like, pretend I can draw a curve, and it would go up. So they intersect right here. To find the intersection value, we go back to this equation. So sine x equals cosine x. Now we know that's pi over 4, but that's the same as tangent x equaling 1. And so x equals tangent inverse of 1, which means that x equals pi over 4. So instead of us having sorry about the feedback. Instead of us having an integral from 0 to pi over 2, which is the area between these curves, we're going to have one integral from 0 to pi over 4, and another integral from pi over 4 to pi over 2. So remember that cosine was the coral graph and sine was the purple graph. So area works as the integral of upper minus lower, we'll say dx. So on the integral from 0 to pi over 4, cosine is above sine. So we're going to have cosine x minus sine x dx. Then we're going to have another integral that's plus the integral from pi over 4 to pi over 2 of just flip it around. So now sine is above cosine. So sine x minus cosine x dx. When we integrate, we should get the same result both times, just flipped around. Whose derivative is cosine? That is sine x. Whose derivative is negative sine? That's plus cosine x, evaluated from 0 to pi over 4, plus this should be negative cosine x minus sine x, evaluated from pi over 4 to pi over 2. The sine of pi over 4, square root 2 over 2. Cosine pi over 4, square root 2 over 2. So we end up with square root 2 minus the sine of 0 is 0. The cosine of 0 is 1. So what's this? 0 plus 1. So you know what? Let's fully write it out. So the sine of pi over 4 is square root 2 over 2. Cosine pi over 4, also square root 2 over 2. Sine of 0, 0. Cosine of 0, 1. So we end up with the square root of 2 minus 1 for the first integral. For the second integral, we're going to have the cosine of pi over 2 is 0. The sine of pi over 2 is 1 minus the cosine of pi over 4, well, negative cosine pi over 4, which is going to be negative square root 2 over 2. And the sine of pi over 4 is also square root 2 over 2. So we have negative 1 minus, what's that, negative square root 2? So plus, so we're adding all of this together. So that is 2 square root 2 minus 2. Now, by symmetry, we could have just doubled this result. We just did it. All right, so that concludes this video on area between two curves. Remember, it is just the integral of the difference of the functions, and they may intersect inside the interval, in which case we split our integral into at least two separate integrals that take into consideration the intersection value.